Good day, and welcome to the Kennedy Space Center. I am D. Wayne Washington from the Office of Communications at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Today we're here to talk about the Robotic Refueling Mission, the module to be carried on the final shuttle mission. Here to explain the mission, to my left, Frank Cepollina, Project Manager for the Satellite Servicing Capabilities Office at NASA's Goddard Space Flight Center. To his left, Mathieu Caron, Mission Operations Manager, Canadian Space Agency. And finally, we have Ben Reed, Deputy Project Manager for the Satellite Servicing Capabilities Office at NASA's Goddard Space Flight Center. We'll begin with Cepi.
Well, thank you for coming. I look around the room and I see a lot of familiar faces. We've been here for the last 20 years, if you all remember, with repair activities, human repair activities on Hubble. But then I really started with you all back in, with Kennedy back in 1984, where we robotically captured Solar Max, and then with humans repaired Solar Max. So the servicing capabilities primarily vested with humans and with robotics started way back, some 35 years ago. And the interesting part about it is here we are today, opening up a brand new era, and I underscore brand new era, in servicing of expensive satellite systems through the use of robotics. And that represents a new major initiative and capability that the global space community is now stepping up to. And I want to introduce our partner, who we've worked hard with at Canadian Space Agency, Mathieu Caron and the Canadian Space Agency, that have been the other part of this U.S.-Canadian partnership. And they are the folks that build the robotic arm, the Canadian robotic arm for ISS, and SPITM, what we affectionately call the Dexter robot, which we will be using on this mission. So this mission does two things, and Ben is going to talk about the details as to how it works. But it focuses on two principal issues. The first principal issue is the ability to capture and repair satellites that have never been designed for in-orbit repair or capture. If you remember, Hubble and Solar Max had elements of designability incorporated into their systems where, in fact, they were amenable to repair via humans. In the present state, there's over 370 some-odd commercial communication satellites in geosynchronous orbit and over 100 government-owned systems, none of which have been designed for repair. Yet what we're trying to do and demonstrate is that the technology and capability through robotics today exists, and by use of the space station external platform, we can, in fact, eliminate or reduce the risks of doing those kinds of tasks robotically in space. And so with that, let me turn it over to Ben. And, oh, excuse me, Matt, it's all yours.
Well, thanks, Epi. Thank you very much. The Canadian Space Agency is very pleased to be collaborating with NASA on this, on the robotics refueling mission. We're quite looking forward to this demonstration that will show that space robots can use special tools and unique maneuvers in order to service satellites, even to the extent of refueling them. And as was pointed out, this mission will be using the Canadian-built Dexter, which is a two-arm robot, which was designed for the space station's maintenance. But this will be the first time for Dexter that Dexter will be involved in such a research and development project, as opposed to the routine maintenance and logistics on board the International Space Station. So in Canada, we're quite proud of our legacy in the field of space robotics. If we look at the Canadarm, which has been on the space shuttle for the last 30 years, we alluded to early satellite servicing missions, for instance, the Hubble Space Telescope servicing missions, where the shuttle astronauts used the Canadarm to catch and retrieve satellites to be repaired before releasing them. So really we had a lot of success with this, and if you look more recently, we've celebrated 10 years of Canadarm2 operations on board the space station. And this anniversary also marked the decade of intense collaboration between NASA and the Canadian Space Agency, as our respective teams of engineers have been working very closely together in the preparation and execution of day-to-day robotics operations. And now if you look with Dexter more recently, even more, Dexter has been used recently for to offload the Konotori Japanese resupply vehicle. Later on this summer it will be used in order to replace a remote power controller module on board the space station. So you can see that that the robotics refueling mission really falls well in line with Canada's own efforts in order to advance the field of space robotics, and falls in line also with the development of our next generation Canadarm project. And basically, one key difference, though, is that so far Dexter has been used primarily in order to maintain devices that have been designed for robotic manipulation. So we're quite looking forward to see how Dexter will perform with those new tools, because if you look at the tasks involved, which are removing caps, cutting through the exterior of the simulated exterior of a satellite, or connecting a hose to a fuel valve, those are all tasks which will present unprecedented demands on Dexter's sense of touch and fine motion. So we're quite looking forward to executing those tasks and seeing basically how we can work together, share our expertise as we tackle these new operations. Thank you.
All right, so now we'll go to Ben, and he'll give us a demonstration on just what the RRM mission will look like.
Thank you, Dwayne. Thank you, Cepi and Matt. My name is Ben Reed. I am the Deputy Project Manager of the Satellite Servicing Capabilities Office. So you heard both Cepi and Matt talk about different satellite servicing capabilities. I like to think of it as a three-legged stool. The first leg of satellite servicing is repair and refueling. So I'm going to talk a lot about repair and refueling in just a minute here. The second leg is in-orbit construction. You have something that's too big to fit in a single rocket, well, you fly up two halves, you join it in space. That's another capability that satellite servicing brings to the agency and to the international space community. The third is active orbital debris removal. The ability to go up and grapple something that wasn't designed to be grappled and then do something with it. Push it up, push it down, dispose of it somehow. So those are the three main legs of the satellite servicing stool. So I'm going to talk a lot about repair and refueling. So I've got 4 wonderful kids at home. They're a little bit older now, but when they were small, I used to buy them toys, obviously, one of which was a Fisher-Price workbench. Right? What comes in the box when you get it? It's a little tool bench with some little plastic nails and a plastic hammer. So the nails is what the hammer hits. You don't get a little arm inside there to control it. That's what the kid provides. The kid picks up the tool, hits the little plastic nails. Well, that's exactly what we have here on our high-fidelity mechanical simulator that we at Goddard built to help us with the RRM module, which is obviously on the STS-135 right now, ready for launch. And just let me pause for a moment to say how humbled and proud we are to be part of STS-135. Could not be more excited to be here for this launch. So here we have our Fisher-Price toy box. At the risk of being misquoted, I'm going to try to stick with that analogy. So what are the nails? What are the things we're going to work on? Well, those are legacy satellite interfaces, interfaces that were not designed to be serviced in orbit. Primarily, I will talk about a fill and drain valve. So satellites that are built around the nation at Goddard and many other places are sent to Kennedy for processing. They are empty. They have no propellant inside when they arrive. They get to the launch pad, and now they're ready to receive their propellant, right? Very hazardous, so we do it late in the flow. So this is what a fill and drain valve looks like. Right? You see a 1/4-inch diameter hole here. So somehow we're going to get the fuel in through this 1/4-inch diameter hole into the satellite, so when it gets in orbit, it's got propellant. So they thread onto this last male threads here. They pump in the hydrazine, monomethylhydrazine, or nitrogen tetroxide. They then rotate this silver nut here, and that closes off an internal seal. Now the fluid is contained inside the satellite. But it's so hazardous, they need extra precaution, right? If that seal were to fail and the propellant were to leak out, very bad for the humans in the area, and we like to be safe. So they put on a secondary cap that provides additional safety, and it is cleverly called a safety cap. So safety cap goes on next. Now we've got two seals, the internal seal and the safety cap. Now they put on safety wire to prevent the actuation nut or the safety cap from inadvertently backing off during launch loads or ground processing loads. They put safety wire to hold it in place. And I'll show you safety wire on the module in a moment. Finally, they put on a tertiary cap. The tertiary cap goes over the whole assembly, and it is safety wired shut. So now we have two fault tolerance. Two of the seals can fail. We've got a third one that will keep the hazardous fuel inside the spacecraft, not where the humans are. So if we're going to undo this robotically, we've got to reverse those steps. So safety wire is the first thing we need to tackle. So take a guess what we call the tool that we use to cut wire. The wire cutter tool, exactly right. So we have a wire cutter tool, and rather than pull one out of the bays where it's stored for launch, I'll show you this one. So here's our wire cutter tool. The wire cutter tool has at the tip of it a hook. It's kind of hard to see, it's on the back side, that we use to hook around a piece of wire. We then use the Dexter robot by our good friends at the Canadian Space Agency, which is holding our tool, to drive the torquer drive, which activates a lead screw inside, and it closes down a little blade which chops the wire in half. So now we've just done our first robotic activity. This robotic activity is controlled via our friends down at Johnson Space Center, a partner with us on the RRM mission. They are flying the robot. They are flying the Dexter robot from the Ficker-1 at Mission Control in Houston. So very tight collaboration with our robo friends in Houston. So we cut the wire, and now we're ready to, we put that tool away. Now we're ready to go after the tertiary cap. Now the tertiary cap, rather than build a tool to go after the tertiary cap, and that be the sole function of the tool, we designed a tool that has multiple functions. So we call it the multifunction tool. So the multifunction tool will pick up one of four adapters. And the four adapters are stored in these four receptacles you see on top of our mock-up here. So we pick up the tertiary cap adapter out of this location. It attaches to the end of the multifunction tool. And now with that tool, we engage the tertiary cap, unscrew it, take it off. So that cap is then stowed in here. And now we've exposed the two safety wires and the safety cap. We pick the wire cutter tool back up. We cut the two pieces of wire here just like we did the first one. And we then use our safety cap tool. And I will remove the safety cap tool just the way the Dexter robot would do in orbit. So this is how the safety cap tool is removed. So here is our 18-pound safety cap tool. It looks rather complex. Let me see if I can break it down a little bit simpler. So the active part of the tool is right down the center. The center shaft is where all the gears, the mechanisms are that allow the Dexter robot to actuate its torquer drive to engage the safety cap and unscrew it from the robot. Well, the robo flyers, as good as they are down in Houston, they have to be able to see what they're doing, obviously. So we have two integral cameras and their LED lights, which allow the robo flyer to see the business end of the tool. So the safety cap tool then engages the safety cap, removes it, and that part of the job is done. So now we have an exposed or naked fill and drain valve. So the safety cap has now been removed, leaving behind a fill and drain valve that looks like this. So now we would need to do the robotic activity to attach to these male threads and transfer fluid into it, just as a spacecraft in orbit would give the customer satellite more propellant. So we use our final tool here, our fourth tool, and that is an embedded acronym. It's the EVR nozzle tool, or ENT. So not an EVA activity. No astronauts involved with this demonstration. It's all robotics, so it's an EVR nozzle tool. And you can see what's different about this one right off the bat is that it has this hose connected to it. Well, Obviously, we have to flow fluid somehow, so we use that hose, which after we thread on to the exposed threads here, we're able to pump fluid through the ENT and into an internal system. We have a series of tanks, valves, latches inside the module that we command through ELC via our other partner in this mission, and that is the Marshall Space Flight Center. We have been working very well with the command team down at Marshall to help us with the commanding that we're going to need to do to flow fluid through the tool into the valve. So I've just gone into a great detail about the steps involved with robotic refueling. We have a lot of other tasks we're going to do on this mission, but refueling is one of them. So I have a video. Now that I've gone into great detail, and I'm sure I've confused all of you, if we could roll the video, please, and you'll be able to get an overview of what the mission is going to look like. Okay. So after launch on flight day 5, we will be picked up by the EVA crew member, the ISS EVA crew member, and transferred over to the EOTP platform. A few weeks after that, we'll be moved from the EOTP platform to ELC4, which is at the far right side of the video screen. Once we are located on ELC4, then the SSRMS, picking up the 2-armed Dexter, will be moved over, just as you see in the video now, and it will begin the operation. So I've talked about the 4 tools that will be picked up. Here you can see in the video that one of Dexter's arms is going in and making contact. So this shows you from a big picture how, at the end of a 55-foot arm, the 2-armed Dexter will be doing the operations. So here you see a split screen. The image in the upper left is the view that the RoboFlyer will get. Right? These are from the cameras located on top. You see the God's eye view in the center of the screen, but you see the tool camera view. So that's the view that the RoboFlyer gets when the operations are being conducted. So you can see that safety wire is mighty hard to see. So it took a tremendous amount of coordination with our tool development team at Goddard, the RoboFlyers at Johnson, the operations folks up at CSA who are building the reconfiguration files for the robot for this. So tremendous amount of coordination was required. So now you see a close-up view of the very end of Dexter's arm picking up the multifunction tool. So the multifunction tool, quiz, anyone paying attention, what does it need to pick up to remove the tertiary cap? The tertiary cap adapter. Come on, I see people in the audience that are on my team. You guys should know the answer. All right, so here we have the tertiary cap adapter, and it is going to go after, you got it, the tertiary cap. Again, the split screen, the window and window, that is the actual laboratory footage sped up tremendously, I might add, the removing of the tertiary cap. So we've done these operations on the ground in the lab many, many times. What we haven't done is these operations in orbit. So that's what RRM is. It's the on-orbit, the zero-G demonstration of robotic refueling of legacy interfaces for the first time. Again, we've done it many times on the ground, but we've never done it in orbit. So that's what RRM. We anticipate it enabling future missions, future capabilities for the international aerospace community. Thank you very much.
All right, so now we'll open up for questions. I'll ask that you wait for the microphone first. When we get there, please state your full name and your affiliation. So we'll begin with the gentleman right in front here. Just
Jim Siegel, Celebration Independent Newspaper. I may be a little slow here. I just kind of wanted to make sure that I understood what you were talking about. So this module is going to be attached to the outside of the International Space Station. Correct. And it's going to stay there indefinitely. Is that correct? It's not coming back, or
planned operations is 2 years of operations. After that is the current plan.
Okay. And then the arm, the Canadian arm,
yes,
would capture and retrieve a satellite. Correct?
Let me correct you there.
Okay.
So rather than bringing a satellite to ISS, That would be rather challenging to do from an orbit dynamics point of view and from a safety point of view. So rather than bringing a customer satellite to ISS, first we need to demonstrate the technology on mock satellite interfaces. So what you see here is a fill and drain valve that is exactly like it would be on a real satellite in orbit. So we are going to demonstrate the capability here before we do it for real on a satellite. So I've seen in the press, it is easy to talk about RRM as a gas station in space. That is the next mission. This mission is to show that the technology exists today, to show that we have the capability today, rather than to start refueling satellites a week from now when we're in orbit.
Okay, so this demonstration module is going to stay attached to the ISS for 2 years.
Yes.
And it's going to be only demonstrating. It's
That's
not
right.
going to be servicing
That's
any
right.
other.
I went into great detail about the refueling part of it. We have 5 major tasks that we are going to do with RRM, but for the sake of time, I focused just on refueling. We have a lot of other interfaces. You can see she's a pretty porcupine, is she not? Well, we've got lots of other tools, we've got lots of other adapters, we've got lots of other legacy satellite interfaces that we are going to practice limited repair and other servicing tasks on it. So I've just talked about refueling today. So it's going to take us 2 years to make it through the entire gamut of planned tasks.
And then is there a timeline for when something like this, an operational phase 2 whatever device, would be attached to the space station? And the idea is eventually, phase 2, phase 3, whatever, to capture satellites and bring them in and service them?
The subsequent phase would be to build a standalone robotic servicing spacecraft to go do real satellites in orbit. Orbit dynamics being what they are, if you're not near a space station, it takes a tremendous amount of fuel to get there. So were somebody to need service in orbit, you send a tow truck to them, or geosynchronous orbit, as my boss Frank Cepollina mentioned, there's well over 400 satellites. They're all at the same altitude, almost the same angle, and going the same direction. So geosynchronous orbit seems like a very logical place to launch the first servicing mission, right? You're not going to build a tow truck on the ground and go off to a country road where cars never come by, right? You're going to put it strategically where you can get to a lot of customers quickly. So were I to be designing a mission to go and service satellites in space, I'd want to go where there's a lot of customers going the same direction to minimize the amount of fuel to get to them, and that would be geosynchronous orbit.
All right, so gentleman right here in the front.
Hi, Ken Kramer, Spaceflight Magazine. Question about the Canadian involvement. I was wondering, when Dexter was launched and conceptualized, was this RRM on the plate, or was this kind of added afterwards? Thanks.
Well, that's a very good question. No, it was not. So basically, Dexter's main mission on board the station is to perform maintenance and logistics operations for components that have been designed to be handled robotically. And clearly, one of the purposes of this demonstration is to demonstrate that you can actually interact with components that have not been designed for robotic manipulation. So I think we had enough flexibility in the system, the ability to interface with tools, to upgrade software, to optimize its performance using specialized robotics configuration files, that allows us to do that. But definitely one of the objectives for us of this particular demonstration is to see just how far we can push Dexter and accomplish those exciting tasks.
Yeah, that must be very exciting. A very exciting avenue for you. Are there any other Dexter operations coming up that are new that you could tell us about?
Well, Dexter really has been in full operation since 2010. It arrived in 2008, but we really started in earnest to operate it for instance, to offload the HTV2 vehicle earlier this year. Next year, later on this summer, we will be changing out a remote power controller module. If you recall, last year we had attempted to do so, but the module did not meet exactly all the required robotics requirements. And but we were able to perform more analysis, and now we're going to continue doing so. So, in a way, all new operations, every new on-orbit replaceable unit we we change out brings us a wealth of additional knowledge for us. If you look just at the operation of Dexter, it originally was conceived as purely operated by astronauts on board the station, and now its primary mode of operation has transitioned over to ground operators. So it's a very exciting time for all involved.
All right, we'll take this gentleman right here.
Yeah, hi, Mike Wall from space.com. So this is actually already, you've already shown this can work in the lab. I was just wondering, what are your kind of thoughts about what the main challenges are going to be in space? What are some of the biggest hurdles that you're going to have to overcome? And how much more difficult is that going to be than what you've already seen it do?
So to answer that question, it sounds like we need somebody with expertise in both robotics and in tools. So I would like to turn it over to my colleague, Jill McGuire. Jill was the tool manager for the Hubble servicing missions, and she is the project manager for RRM here. So Jill, would you help me answer this one?
I knew that Ben prepped me to say he was going to turn a question over to me. I see he decided to give me the hard question, save the easy ones for himself.
I'm no dummy.
So just to make sure I understood what you asked, the biggest difference between doing this in the ground in orbit, what we can expect, the biggest difference is really in the orbital dynamics, or how the contact dynamics. On the ground, we can control it when we interface to this. We can't 100% control that in space. And if you think about when we use the Dexter robot, it's on the end of the Canadian Arm 2. So you've got the dynamics in play between the Canadian Arm 2 and the SPDM robot, and then our tool. So when you have all of that dynamics coming into play, there's going to be some oscillations. So trying to downplay that or figure out how you can react to the spacecraft, the interface when you touch it, is the biggest thing. So we built a contact dynamics facility at Goddard where we simulate the dynamics that we expect to see on orbit, so that when we practice on the ground, we have those dynamics simulated, so we know how the tool will react when it touches the spacecraft. So one of the key aspects of doing this with the SPDM robot is after we do this on orbit and we learn how the tools react to the interface, we can then get ground characterization of our ground test bed, or characterization of our ground test bed, excuse me. So that will be the key thing, is really the on-orbit dynamics that we don't have 100% simulated on the ground.
All right, thank you, Jill. We'll take this gentleman right here.
James Dean with Florida Today. Can you identify the satellite that you're planning to service and when, and when that time comes, is there a possibility you're going to add customers, or is that just going to be a one-off test?
Well, it's it's not our role to try to usurp commercial industry. What we're trying to do here, although we have looked at a whole different family of satellites with different end effectors, different fuel valves, different kinds of appendage deployment issues, and so on. What we're trying to do here is to demonstrate that we can, in fact, apply the technology so that no matter who does it, and we're going to make this data available to everybody, that is all commercial industry that may want to leap off and start their own ventures, make that technology available, allow them to understand what the risks are, what the problems are, and to, in effect, try to consolidate or try to reduce the risks of in-orbit repair and refueling and maintenance and supersinking to the greatest degree possible by being able to demonstrate on this kind of activity that we're running from station, and therefore give everybody the encouragement that's necessary to get them rolling. And there's all kinds of historical analogies and reasons for doing this. If one recalls what we all depend on today with BlackBerries and iPads and iPods, and is bandwidth, is COM bandwidth, and bandwidth is expanding exponentially year after year after year, and the need for it. And so what we're basically trying to do is to provide the encouragement to different operators and users to design their satellites and to perhaps design, build, and fly missions that can take care of the normal repair, maintenance, and refueling that would normally be required. And without such a thing, the satellites that are not getting this support or getting this kind of support would end in the end in failure, or would end their lives either abruptly or short of a full expectation of utilization. So really, this is a level of maturity for space and the space agency to help accelerate this maturity level and demonstrate this maturity level to give people like the Telstar people in the early 60s the confidence to get going with a commercial communications satellite industry. And that's what, in fact, has happened. That's what NASA's role is. Give potential users the confidence to go ahead, take the risks, leap forward, and for all of mankind to receive the benefits. 10 years from now, the amount of bandwidth required, if the rate of expansion of iPods and Kindles and everything else in computation in the sky, in the clouds, if that expands at the rate we're going to be 100 times more in need 10 years from now of bandwidth than we have today. Can you imagine what that says about communication satellites and how to handle them and how to maintain them and how to protect them and how to use them? And even more important, we pay X number of fractions of a cent per data bit that comes down. Can you imagine what would happen if the numbers of communications bandwidth capability were to expand? It would be a supply-demand kind of ratio, and you would lower the cost of operations. And that's significant for you and me and everybody.
So your intent is to basically turn over like an RRM type device to a commercial user that would like integrate
the technology,
something other than Dexter to
the technology. We're going to make this technology available. Yeah, you wouldn't turn RRM over, but you'd turn the technology, the type of tools, the approach, the lighting, the cameras, the tele-robotic feedback, those kinds of things.
Okay. Right here in the yellow shirt. Wait for the microphone, please.
Question for CSA. Matthew, does that mean that the Canadian Space Agency and McDonnell Detweiler technology of Dexter would also be turned over to commercial affairs?
No, right now the plans is we're operating RM exactly like any other operation on the International Space Station. We're, participating in the flight control and the production of mission planning products and so on. We're performing the analysis. So basically, the involvement of McDonnell Detweiler and Associates as a primary contractor to CSA for the International Space Station, they support us. They provide us with the engineering support that's required to perform these tasks as we would for any other maintenance task on board the space station. In parallel, what we're doing is that we have put up there's in works a next generation Canadarm project where we're developing terrestrial prototypes for robots and effectors, tools, and so on. But at this point, it's basically the current state of our projects.
All right. So, gentlemen in the front row here.
Hi, Mark Kirkman, Interspace News. Actually, a two-part question. In dealing with or in regards to the space refueling, do you kind of envision this, using this initially at least with satellites that are at the end of their life cycle? Because I can foresee a scenario, for instance, you go up there with a satellite and you manipulate a valve that hasn't been operated since it left the ground, and now all of a sudden you're leaking gas. Also, the second question would be, is there any effort in the industry now? I mean, is it too early to kind of standardize these types of fittings so that as this technology is developed, you can deal with the new spacecraft that are being launched? Are they standardizing these fittings, the fuel valves, et cetera, et cetera?
From the point of view of standardization, most of the valves that are manufactured and built today are very, very much the same kinematic principles. The only thing that's different about them is dimensions. For the most part, from a refueling perspective, we noticed that commonality has happened in the aerospace industry over the last 30 years, 40 years. is really maybe a driver for consolidation and cost control. But there is very, very difficult to try to standardize anything in space in this arena because every aerospace manufacturer of satellites has his own unique approach, and no way, no how do they ever want to give that approach up because it's endemic. So where does that leave repair and maintenance in orbit, which is really the heart of your question? We have to be dexterous enough, we have to be general purpose enough with the development of our tools so as to be able to demonstrate that you can do more than one straightforward task on more than one kind of satellite, on more than one kind of fill and draining port, and perhaps maybe on more than one type of array or one type of communications antenna that didn't deploy. Now, the mix is of how many satellites. The first question you asked was, what about the old bird that's up there and you try to refuel? It's been up there 20 years and you can't do it. Well, the one thing you can do is you can supersync it with that kind of tow truck sort of capability. You can take it out of orbit, so to speak. So those are the kinds of thought processes that one has to come to grips with when one starts to think about developing tow trucks in orbit that can take care of expensive assets. That's key, and one has to think about the ability to leave that asset, leave that tow truck in orbit long enough for several or quite a few different spacecrafts that get into trouble to take advantage of it. And it's not going to be able to be all things to all people. It's not going to be able to be that. But there will be, as a result, enough competition and enough interest, I feel, that you'll have more than one supplier. And that's all very good. I mean, you have DLR in Germany that's looking at similar approaches with DIOS. You have the Japanese that have done even some demonstration servicing on some of their payloads. You have Canada and MDA that are very much interested in doing that. And yes, I'm sure we're going to have American communications companies that are going to stand up and take an interest. But that's all well and good. Where would Ford be today without Chevrolet? Competition is wonderful. And that's the important message here. And what you have to do to get competition started is reduce the risks that they're walking into. Reduce the risk. And that's what RRM represents. It's a risk reduction technology demonstration. Probably from a space station perspective, the most practical demonstration of the worth of station from an applications perspective, not medical, not physiological, not metallurgical, but applications. What does it bring as a demonstration to you and I 10 years from now? That's the key. That's the key. We have to have the ability to look forward. We have to look beyond today and tomorrow and keep stretching the technology. And that's what space station's about. It gives us that applications technology capability to push the envelope, to get us out in front. Yes, one day we're going to fly a neurosurgical robot that will do operations on astronauts from the ground. They do that today, and it's called Da Vinci. And the Canadians have one, and I'm at a loss to tell you what it's called, but 10% of our hospitals today in the United States have Da Vinci robot surgical instruments. Are we going to have that 10, 20, 15 years from now when we send our astronauts away for a couple of years to distant locations? If we keep this up, I think we will. But this is truly applications, demonstration capability.
All right, take this gentleman right here. Yes.
Yeah, I'm Peter Wright with the Canadian Press. You talked very, very shortly about reducing risks. Now, over the past few years, we're seeing satellites starting to crash into each other. I just wonder if there was any urgency to do this in light of the fact that there are a lot of satellites that are reaching their best before date. There are satellites starting to crash into each other. There's a lot of concern about that. I wonder if that prompted you to speed things up a little bit.
I think that was one of the factors. I think clearly when those two satellites collided, that clearly orbital debris. I think there was another satellite called Galaxy 15 or something that temporarily drifted out of control, and all the other communication satellites were jockeying their positions and handing off comm responsibilities because they wanted to get out of the way before they got hit. I think all of those kinds of things are what's going to happen tomorrow and the day after and the day after. And the more satellites you put up there, which you're going to have to do to cover bandwidth, you're going to have to do it, the more probability there is that you're going to need a tow truck. And interestingly enough, probably more than one. Probably more than one. I think quite a few. And they're going to have to stay there and be on call when you want them. Okay.
All right. Thank you. Got a follow-up question right here. And then I'll do that.
Jim Siegel again from the Celebration Independent. With respect to these tow trucks that you mentioned, roughly what time frame would you see this happening? 2025, 2050, where these commercial tow trucks, let's say Gerhard wanted to start his own tow truck company and use your technology, he's going to put it in space, he's going to go around and service satellites. What kind of time frame are we talking about?
I wish you were here in 1984. You know, I can't. I think the time frame is the next 3 or 4 years, 5 years. We're going to have to be there, done that. And I maintain that by this kind of technology, when I say we, it doesn't necessarily have to be NASA. It does not have to. It could be commercial from any place around the world. I think the business space will start to demonstrate itself. But don't forget, I was here in 1984, and we had a screwy mission, a very never been done before mission called the repair of Solar Max. Does anybody remember that? You weren't born then. Oh, some of you were. Okay. Geez, nuts. I always thought there was an advantage to being old, but guess what? Nobody ever envisioned that we would capture Solar Max with a robotic arm. Nobody ever envisioned it. And some idiots who had some forethought at Goddard decided that before they launched, they would put a grapple fixture on that spacecraft. But that spacecraft was not going to be captured by that grapple fixture. No, no, no. That was just a risk mitigation device, whatever you want to call it. That was a contingency. No. But when we tried it the old-fashioned way, we discovered contact dynamics like we had never seen them before, involving humans and free-flying spacecrafts. And guess what? It was solved by a robotic operation of something called the Canadarm for the first time. And after that, guess what? We never bothered to deal with capture of spacecrafts any other way with robotics. So technology is there, technology is coming. The issue is how do we apply it? And how do we demonstrate its application so that it minimizes risk? RRM is that way. And there'll be other missions like RRM that'll come after that that will drive from station the ability to demonstrate reduction of risk.
All right, we're but just about out of time. Real quick, can you get your question in really, really quick?
Randy Atwood again with Spacecraft Interactive. Also back in 1984 on the 13th mission, 41G, there was an EVA and there was a demonstration of refueling. Were there any lessons learned from that or any applications from that?
The biggest one of all was 5 Hubble servicing missions, a GROW recovery mission right after deployment, CINCOM 4, Intelsat 6, West Arm Palapa. There's a total of 11. Yes, we learned a lot, and I think we're going to learn a lot from here.
Okay. We're running out of time. If you got more questions, we can deal with the questions a little bit later. You'll have a chance to talk with Seppi and Ben and the module affectionately known as Rosie. So that concludes our demonstration for today. The next event on NASA TV is the Multi-Purpose Crew Vehicle Demonstration tomorrow morning at 9 a.m. And for more information, you can always go to www.nasa.gov/shuttle. Thanks, and have a great day.